Okay, I think we are live, so we can start. It's my pleasure to introduce Lucas Muller. He is computer science bachelor student in his 5th semester, and he is interested in low-level programming and interactions between hardware and software. Lucas is going to present SIMDRAM. To me, is a very relevant work in one of the main trends in processing in memory that we call processing using memory. And SIMDRAM enables a way of processing using memory in a SIMD fashion and gives us the ability to create complex operations inside DRAM. So I think that this is a very interesting work. I hope it goes very well, Lucas. Thank you.
Thank you for the introduction. Let's start right away. Today, I'll be presenting SIMDRAM, an end-to-end framework for bit-serial SIMD computing in DRAM. This is a paper by the Safari Research Group, by the main authors Nastaran Hajinassa and Gerardo Oliveira. It was published in ASPLOS 2021, which took place this April from the 19th to the 23rd virtually. Let's start out with an executive summary. So the motivation for this paper is that existing processing using DRAM proposals like AMBIT either mostly focus on basic bitwise operations like AND or NOT and those, and aren't flexible enough or require significant changes to the DRAM subarray. The observations that the authors of SIMDRAM make is that shifts can often be eliminated by changing the data layout, and that two prior works, AMBIT and RowClone, already provide the necessary primitives to implement complex operations. Their goal is to provide a framework that aids the adoption of processing using DRAM by efficiently implementing complex operations and providing the flexibility to support new desired operations as needed. Their main idea is to build up complex operations from those basic primitives used by AMBIT and RowClone, and offloading some of the scheduling work to a separate SIMDRAM control unit, which lives inside the CPU. The evaluation will show that at a very low area cost of only around 0.2% of a modern CPU, SIMDRAM can effectively achieve higher throughput by multiple magnitudes sometimes compared to modern CPUs and GPUs. It also is multiple magnitudes faster, more energy efficient than a modern CPU, modern GPU, and AMBIT as a prior work. This will be the outline of today's talk. We'll start out with the problem statement. I go over RowClone and AMBIT one more time, although we already discussed it in class in a prior session. And then I'll go over SIMDRAM. And we'll end with strengths and weaknesses and hopefully a good discussion. Let's start out with the problem statement. Data movement is currently quite inefficient and slow because we have to use the bus, and sometimes the bus is full and thus we have to wait for it. And modern applications can be quite data intensive, which means that we lose a lot of efficiency when we move data from DRAM to CPU and store it and load it back. And doing computations on large amounts of data can thus be very slow. A lot of these data-intensive computations are so-called data parallel, which means that we do computations on each single element of an array or combine multiple arrays at the same indices. For example, adding two arrays up would be a data parallel operation. Traditional SIMD, which also gives this paper its name, speeds up processing in the CPU by allowing single instructions to modify and multiple data values. but the memory movement overhead still exists and makes the process inefficient and slow. Existing processing using DRAM proposals mostly support bitwise operations like AND and OR, but real-world kernels can be much more complicated. Thus, the scheduling and chaining all of these primitives can be the bottleneck. Let's get to the background. I already mentioned row clone and Ambit. Let's see what those are. First of all, this is a schematic representation of a DRAM system. We have a processor on the top left-hand side with the memory controller, which communicates over the memory channel with our individual DRAM ranks. In there, we have chips which contain subarrays. In these, the data is stored in DRAM cells. Let's look at a subarray in more detail. We can see that a DRAM subarray is made up like a grid. We have a row decoder, which can set the word line to in specific locations. And we can see that we have a bit line here represented vertically, which connects all of the bits vertically to connect to the sense amplifiers. There are two main DRAM commands which are important for today. Activate and precharge. Activate will select an individual DRAM row using the row decoder, making the word line high and thus connecting all of the DRAM cells in that row with the bit line. And we have precharge, which resets the row decoder into its default original state, and also gets the state, the voltage back to VDD 1/2, so that the sense amplifiers can do their job again. Row clone now exploits the already existing behavior of DRAM by first activating a single row we want to copy from one row to another. This means that the sense amplifier will amplify the value that is stored in that row. And then in the second step, it will activate a second row. The sense amplifiers will store the value into the row, and thus the data is copied from the first row to the destination row. Then we have Ambit. Ambit does something pretty similar. It does a so-called triple row activation. Instead of activating 2 rows after each other, we activate 3 rows after each other without preloading in between. That means that effectively we're connecting all of these capacitors with each other in each row. So in this example, we would be connecting directly 3 of the DRAM cells with each other. This means that the slightly negative and the slightly positive charges will cancel each other out. And for example, for 2 slightly positive charges and 1 slightly negative charge, we would get a slightly positive charge with which the sense amplifier can then amplify and turn into a clean value. So the result is that we have 3 inputs in every column, and the majority operation would be executed for each of them, and the result would be stored in each of these rows. The majority operation is a Boolean operation which takes 3 Booleans as input and returns the Boolean as output, which is more common in the input data. Ambit also divides each subarray into 3 different parts: the D group, the C group, and the B group. The D group stores our normal data, and this is also why it's called the data group. There we would store like our regular application data and our operands for our DRAM operations. Then we have the control group with 2 constant rows, one which always stores zeros in all of the DRAM cells and one which always stores ones in all of the DRAM cells. Then we have the compute rows, the bitwise groups, the bitwise group with normal cells And also these dual contact cells, they allow inverting the input of the other cell. So this is one cell made up of two cells so that we can get the inverted data back out of the cell. Then we have also two different row decoders, a regular row decoder, which can just activate a single cell, a single row each time. And we have a B group row decoder, which is capable of triple row activation and thus doing computations in this part of the subarray. And of course, we also support row clone between all of these cells so that, for example, we could copy C0 into T1 using row clone. That would be it for the background. Let's get to SIMDRAM itself. The goal of SIMDRAM is to design a framework which aids the adoption of processing using DRAM. And at the same time being an end-to-end framework, which means that the programmer can effectively use it, and it's from the API side to the hardware memory side, everything is described by SIMDRAM. It supports complex operations which can easily be extended if new operations are needed, and it's low overhead. And only minor changes to the DRAM layout are needed, exactly those which are already described by Ambit and RowClone. And as I said, it proposes hardware design changes, but also an ISA extension and a high-level C API, which can be used to program with SIMDRAM. One of the key ideas of SIMDRAM is that bit shifting operations, which are essential for many complex computations like addition or multiplication, are hard to implement using the existing data layout. And we get back to that in a second. It furthermore relies on Ambit, which can also already do row-wise majority and NOT operations, and RowClone for fast intra-subarray copies. And for the bit shifting operation problem, we can use vertical data layout to circumvent the need for most explicit shifting operations. And by eliminating those shifts, we can do that by simply changing the index of operands. And based on that, we can do complex operations by chaining majority and NOT operations. Let's get into vertical versus horizontal data layout. Normally, a CPU would lay its data out like this in DRAM. So each element would take up consecutive bits in memory. This means that by simply activating a specific row in this DRAM schematic, we could get an entire element of that array. This makes it easy to access single elements and change single elements. Vertical data layout, on the other hand, does it exactly the other way around. We would store all of the first bits of each element consecutive in memory, then only after that the second bit of every element, and so on. This means that we can get very efficient queries on specific bits of all of the elements, and could for example, say, set the second bit of all the elements to 0. And we can also efficiently implement shifts by swapping rows in the DRAM layout. Let's look at how we would add a new complex operation to our SIMD framework. Let's start out with a simple circuit we can see here on the left-hand side. This is a full adder implementation using 2 XOR gates. The first step would be to implement this same circuit using AND, OR, and inverter gates. We know that this is functionally complete, and in this way, every circuit can be converted to an AND or inverter implementation. Now, SIMDRAM proposes a 3-step process which allows us to implement new complex operations into SIMDRAM. We start out with an AND or NOT logic, and then in the first step, we implement it using majority and NOT, and then generate a so-called microprogram, which we can then execute using our new SIMDRAM control unit. Right, let's get into a bit more detail here. The first step, efficient majority NOT implementation. It takes an AOIG graph, an AND or inverter graph as input. And we simply replace each of the ANDs and ORs naively with a majority equivalent. So we can see on the right-hand side, an AND gate can naively be replaced by a majority gate by simply adding a constant 0 as the third operand. And similarly, we have the same thing with OR by simply adding a constant 1. The result is then a MIG, majority inverter graph, where the nodes in the graph are majority operators and the edges are the movement between different operators, and these can either be inverted or not inverted. We can then optimize this MIG using a greedy optimization algorithm, which is described in the paper. It simply describes which equivalences there are in MIG graphs and how we can replace certain parts of a MIG graph with more efficient parts. Let's get back to our example. We had the AND or inverter implementation here. We would simply place a majority gate over each of the AND and OR gates and add inverters where needed. And then we can optimize the majority inverter graph using the greedy optimization algorithm, and we'll then get to this result, which only uses 3 majority gates, whereas previously we needed many more than that. Now that we have this efficient majority inverter graph, we can generate a microprogram from that. To do that, the first step would be to compute rows in which the operands will be allocated. We can do that by going through all of the majority nodes, starting out with the input elements and going into the direction of the result, using a kind of breadth first search. Following from that, now that we have the allocation to the rows, we can generate a naive sequence of activate precharge and activate precharge instructions. AP is here signaling that we want a triple row activation at a certain row. And now that we have that, we can see it on the right-hand side here, our allocation. We can simply go through the majority inverter graph one more time in the same direction and simply emit AP instructions for each of them and insert AAPs where we need to move data around. And of course, for n-bit operations, we also need to add code which executes the code multiple times. So now we had a single bit full adder, but when we wanted to add 32-bit numbers, we would have to add code around these activate precharge commands to repeat all of these commands multiple times, for example, 32-bit times. And the result of this microprogram generation is then stored in memory so that the SIMDRAM control unit can read it from there. Okay, let's see how operators are executed. When we introduce new ISA instructions, a so-called BB op is important here. When these occur on the CPU side, the instructions are issued to the SIMDRAM control unit. And the SIMDRAM control unit then can issue commands to the memory controller and as such orchestrates the execution of the complex operation. The SIMDRAM control unit pretty much works like a naive simple processor. It has a program memory, it has a program counter, it has special micro registers, and it executes micro programs which are made up of micro operations. There are micro operations which are sent directly to the DRAM controller, such as AAP and AP, which we already saw previously. And there are some which are executed in the control unit itself to modify registers, to influence the execution of the program. For example, we have two control operations, branch not equal 0 and done. But there are also some arithmetic ones like subtraction. This would be a diagram of the SIMDRAM control unit. Let's get over it really quick. We have the BB-op FIFO where new operators come in from the CPU. Then we need to load the microprogram from memory, store it into the micro operation memory where the currently executing program is stored. We also have the micro program counter there, which is incremented every time we execute a command. And we have the micro operation processing fine state machine, which orchestrates execution and sends the necessary commands to the memory controller. We also have a loop counter here, which takes care of arrays which are longer than our DRAM row width. Now let's get into system integration. We know how to generate microprograms, but how is that integrated into normal C programs? SIMDRAM is thought as a supplemental way of doing modifications to memory. And we already saw that SIMDRAM works on vertical laid out data, whereas CPUs and GPUs generally prefer to have their data in a traditional horizontal layout, because only in that way they can quickly get and modify certain elements at a specific index. So, because we need to have both SIMDRAM and CPUs working on the same data, we need to have some sort of interchange between these two formats. And software, of course, doesn't work here, because then we would still have all of that data movement. We would need to load all of the vertically laid out data into CPU just to transpose it and loading it back in. Then our entire process would be for nothing. So instead, SIMDRAM also introduces a data transposition unit, which sits in between the last level cache and the memory controller. And it ensures that all of the data is horizontally laid out in cache and vertically whenever necessary in DRAM. The object tracker, which we see in the middle here, tracks which objects are used by SIMDRAM and will then ensure that the transposition is made whenever necessary. So when the last level cache requests a write back, it will check whether the affected memory location is a SIMDRAM object. When that is the case, it will use the transpose buffer to transpose the data and only then write it back into the memory controller. And in the other direction, when the LLC issues a read request, it will see if that is a SIMDRAM object, and if necessary, transpose it before returning it to the last level cache. And we can use the BB-op transpose init operator to add a new object to that object tracker. They also introduce several other ISA extensions. Namely, there is a BB-op transpose init operation, which you can give an address and a size. And then there are one input operations like BB-op _ negate. And then there's two input operations like add. And we have also a predication operator, which can be used to implement if-else based on a per element basis. For C code, there are two envisioned ways to use the API. Obviously, there are functions which directly execute these new instructions. But they also mentioned that it could be possible to make these optimizations automatically by a compiler. And at the end, a C program using SIMDRAM could look like this. On the left-hand side, we can see that we are allocating 3 arrays, an array B, and an array C, and also a predication array which stores which of these should be used. And we calculate the condition, and based on the condition, either add A and B or subtract A and B, storing the result in C. And we can do the same thing with SIMDRAM by calculating both the results of line 9 and line 11 for all of the elements, and then using the predication operator to selectively take the correct elements either from D or from E. Right, let's get to the evaluation part. Okay, one sec, I'll quickly switch slides. I'm very sorry that this happened. Right, the evaluation is entirely simulation-based using the Gen 5 simulator, and SIMDRAM was compared to an Intel Skylake CPU optimized for AVX 512, and the GPU that was used for evaluation was a NVIDIA Titan V. We also have 3 variants of SIMDRAM compared here. The number after SIMDRAM specifies the number of banks used for computation per channel. Channels usually have 16 banks in this configuration, and this is the number of banks which the memory controller can issue commands to. And we can see that for operations which are linear in size, that SIMDRAM performs really well. Yeah, obviously faster than a CPU everywhere, and also SIMDRAM 16 is faster than the GPU everywhere. And we can see that it is also more performant than Ambit in all of these cases, because Ambit doesn't have these optimized triple row activations and instead has to do the triple row activations with constant operands because the optimization algorithm isn't implemented there. For class 2 operations, we can see that SIMDRAM doesn't perform as well anymore, and this effect worsens with quadratic operations. On the right-hand side, we can also see how this scaling is affected when the element size changes from 8 to 16 to 32 to 64. Linear in size means that the naive implementation which we have to use using SIMDRAM has to go through all of the elements once, and for multiplication and division, we have to go through the n elements n times to compute the result. Yes, please.
Yes, so for class 1 if-else case, Ambit is faster than SIMDRAM. And similarly for class 2 or _red case, Ambit is again faster. I mean, it's just a tiny fraction, but I don't understand how is that possible.
I have to admit that I don't have a good explanation for this. I could imagine that the slide overhead we have, because we have to go through the SIMDRAM control unit and everything like that, could be an issue here if the Ambit implementation is already efficient.
Okay, yeah, I guess. Can you please explain the logarithmic and quadratic classes once again? What exactly does is logarithmic the complexity of the algorithm or something else?
It's the complexity of the bit serial implementation we have to use with SIMDRAM. So the algorithm we use is logarithmic in time.
Okay.
Whereas the CPU might use other instructions to do the same tasks.
All right.
So this also shows why for multiplication and division, SIMDRAM doesn't really perform that well, because CPUs and GPUs have specialized instructions just for multiplication and division, whereas SIMDRAM has to use the naive approach where we have a giant AND and OR implementation and convert that into a MIG that makes SIMDRAM inefficient. No, not inefficient, slow in this case.
Makes sense. Thank you.
And of course, if we have more elements, this effect worsens. But still, SIMDRAM outperforms 3 state-of-the-art baseline systems in most cases, and the throughput drops with increasing element size, since we have to do more work when there are more elements, whereas CPUs might have specialized instructions. Energy efficiency-wise, SIMDRAM also performs pretty well. This is mainly caused by avoiding the costly off-chip round trips to load store data from memory. We don't have to load data into CPU because we are directly operating on memory. And we can exploit the abundant memory bandwidth, which we are not using because we are using SIMDRAM. And in comparison to Ambit, we are reducing the number of required triple row activations by leveraging the optimized majority-based implementation, which is using the 3-step process we saw earlier. We can see that multiplication and division didn't achieve high throughput, but because the energy efficiency is still superior, it might be an option to use SIMDRAM also for these slow operations. SIMDRAM really is energy efficiency doesn't depend so much on the operation which is used. Lastly, the effects were also evaluated on real-world kernels. We can see that a variety of real-world kernels was chosen here for evaluation. We have 2 database kernels with bit weaving and TPC-H query 1. We have k-nearest neighbor as a classification algorithm, various convolutional neural network implementations, and brightness as an image processing function. And we can see that everywhere at SIMDRAM 16 is faster than the GPU, and this is a great sign. And we can conclude that SIMDRAM is an effective and efficient substrate to accelerate many commonly used real-world applications. Right. The paper itself already mentions some limitations, which I want to go over really quickly. It can't really do floating point operations because for those we need variable shifts. So for example, we could shift all of the data 3 bits to the left, but what we couldn't do is shift the 3rd element by 3 and the 5th element by 6. This is pretty hard to implement with SIMDRAM, but for IEEE 754 floating point numbers, we would need that, for example, for renormalization. Shuffling across bit lines is also not supported, and we can only do these limited kinds of shifts using vertical data layout. And synchronization and concurrent execution is also limited right now because no synchronization primitives are implemented. Although we could, in theory, schedule multiple SIMDRAM programs at the same time to different subarrays. This would be supported by SIMDRAM, but without synchronization and concurrent execution, this isn't too useful. Let's conclude the summary. The motivation was that existing processing using DRAM frameworks are mostly focused on bitwise operations and thus aren't flexible and require significant changes to the DRAM subarray. And our observation was that we can often eliminate shifts and that we can use Ambit and row clone as primitives. Our goal was to develop a framework which makes processing using DRAM easier to use and more efficient, and at the same time allowing hardware manufacturers to introduce new desired operations. The idea was to build up complex operations from basic operations and scheduling, triple row activations, and copy instructions using the SIMDRAM control unit. At the end, we saw that SIMDRAM has very low area cost, around 0.2 millimeters squared, when I recall correctly. And both throughput and energy efficiency wise, it's superior to CPUs and GPUs in many cases. Let's get any questions before I continue with strengths and weaknesses.
Just one question. So I guess we can discuss it later as well, but do they mention what kind of compiler optimizations are possible, or do they discuss what kind of optimizations might be applied to improve the benefits?
So in principle, the optimizations would be similar to what loop unrolling already does. And it would simply do loop unrolling with a certain factor. And then we could automatically find instructions which we have implemented in SIMDRAM. So for example, if we see that the user is adding two arrays together, we could add the SIMDRAM instruction there.
I didn't quite understand how the transformation, how the transpose unit works exactly. So you tag a memory area and you say it should be transposed, and then it copies the memory into the transpose unit and copies it back, or so.
No, the transposition unit sits between the cache and memory. So for the processor, it always seems like the memory is laid out horizontally, but in memory, in reality, it's stored vertically. And the unit transfers requests so that they are rotated like that, transposed. So when the CPU does modifications to that memory area, it would transpose that request, that memory area, write that into there where the element changed, and write all of that back.
Okay, so you have to specify in advance when you allocate the memory. You have to specify if it's vertically or horizontally.
No, because the CPU always wants horizontal memory, horizontally laid out memory, and for SIMDRAM we always want vertically laid out memory. So we just tell SIMDRAM, like the control unit, oh yeah, let's lay that out for SIMDRAM, and then it will do that transformation whenever needed.
Okay.
So we simply, let's get back to the C code maybe. We simply, like, it's in the dot over there. No, that we have like line 5 to 7. We simply tell the transposition unit that we want these 3 arrays to be used for SIMDRAM, and then every write request that the processor now makes is done using the transposition unit. Yes?
Wouldn't this destroy the row buffer locality?
Yeah, it does a bit, yes, I guess. But we can get to that in the discussion part, I guess.
Well, I suppose it would. No, this is not a discussion, but I suppose it would destroy the row buffer locality if you. There's a reason.
But the idea is that you mostly use the memory either in SIMDRAM or using the processor, and when you don't need SIMDRAM anymore, you can undo that transposition. But in the meantime, you hopefully did as many SIMDRAM control stuff instructions that it's worth the transformation. But it's still better than doing that transposition in software. Okay, that was limitations, conclusion, outline. Okay, any other questions? Then let's go to strengths and weaknesses. First of all, as a strength, I see that this is a very well-written paper. I can only recommend it. It's a good read. And the evaluation especially is very detailed. They have a detailed comparison to duality cache, which is a competing proposal which doesn't do processing using memory in DRAM, but instead does processing using cache. So that comparison was very interesting. And they also compare SIMDRAM to CPUs and GPUs, which are using modern hardware, which is, in my opinion, a very fair comparison. And lastly, I really enjoyed that they tested it using real-world kernels, which seemed to be applicable. Like convolutional neural networks and database queries seem to be real-world kernels which can be used in applications. As for weaknesses, I think that the process of how a microprogram can be obtained is explained really well and in detail, but the process is quite complicated and is only viable for hardware vendors, really. So whenever the hardware vendor decides that they want a new microprogram because that instruction might be useful to the programmer, and then they would have to go through the three-step process. But it's not feasible for end users to go through that process. It claims to be end-to-end, but some details about memory allocation are left out. So they explain really well that it works with virtual memory and how page faults are handled. But what I didn't see in the paper was that operands have to be stored, of course, in the same subarray, and how that problem has to be solved isn't laid out. And it's also unclear how this would perform in a multi-core system, because when there's only a single SIMDRAM control unit, how would the different cores effectively share the control unit? Would there be multiple control units? I would be interested in further research in that area. And there are also no notes about scaling this in SIMDRAM control unit, whether it becomes a bottleneck at some point, or whether it's fine as it is. I could see that it would be interesting to work on that, or some details would be interesting. With the strengths and weaknesses part finished, let's go over to discussion. My first question would be, what types of applications could benefit from SIMDRAM? We also already saw some examples, but could you imagine other examples which could benefit from SIMDRAM?
Not exactly to this point, but to your weakness point.
Sure.
Was the paper did that outline a process how a user could potentially, even if it's like a complicated process to obtain this microprogram, is there a process to feed the microprocess to the?
The problem is that you need an instruction to give to schedule the program to the SIMDRAM control unit, and for doing that you would need to add a new ISA instruction.
Okay. Yeah.
Which is of course possible, but not really feasible for end users.
Yeah. Or what they could do is have like a generic ISA instruction, and then that tells like, okay, you want to schedule a user U program number 4, and then you just have 4 as a parameter.
Yeah, exactly. That was my idea as well. Like just giving a memory location where the microprogram is stored, and then it would load that from memory, just like it does right now. But instead of having an ISA instruction specifically for that, having one generic one, where the user can just put the SIMDRAM program wherever it wants.
Is there a reason why they have the hard-coded U programs in a memory location? Isn't that a potential bottleneck?
Not really, because I went over it pretty quickly, but there's a scratch pad which stores most recently used microprograms. So we can see here that I think there were like 64 programs which are stored in the scratch pad, and then they are only loaded when they're needed into the micro op memory.
Okay, thank you.
Yes, so I would say, a related question to the first discussion point. Essentially, SIMDRAM is being proposed as a general purpose. I don't know, would you call it general purpose? Because you're not supporting and or not. So fundamentally, all operations are there. So you can theoretically perform any operation inside memory.
But where would it make sense to use SIMDRAM?
Yeah, I mean, the immediate thing which comes to mind is bulk bitwise application or bulk bitwise operations and applications. And I guess that is the target group, but I'm thinking a bit different. So do you think it's possible to execute a complete application regardless of the performance? Let's keep the performance aside. What if I try to execute an operating system or a complete application inside this memory? I mean, okay.
My microprograms are limited to 64 operations in size. So you would need many of these microprograms and chain them after each other.
Yeah, but still, that is like a completely new way of doing things, right? Till now, we have been thinking only about von Neumann and CPUs, but if you could do the entire thing in memory, regardless of performance, I mean, let's just.
But where would the difference be to just issuing write commands directly? I mean, you can already have that, like simulating the operating system in memory if you simply issue write commands. Or is your idea? Yeah, right. I think the point that you don't have yet is that you can conditionally do stuff based on memory locations. So of course you can have the predication operator, but that typically only does and or. So it doesn't. You can't execute a SIMD program an amount of times based on what is in memory. If there's like a 32 in memory, you can't execute something 32 times because there's a 32 in memory. You have to tell it what to do in advance.
Oh, sorry. That basically means the code size is larger. The instruction stream is just duplicated.
But you don't really have if and like while loops or so. Of course, you have constant sized loops, but you don't have if and else, which makes everything like really inefficient.
Yeah. Okay, I guess. Yeah, I mean, this can be something interesting. Okay, thanks.
But an interesting idea for sure.
Wait, can you conditionally, can you do anything conditionally in SIMDRAM?
You have break not equal 0 instructions, and you have micro registers which store values in SIMDRAM control unit, but you can't combine both of them.
So I can't.
You can have like registers in your SIMDRAM control unit and based on that do stuff, but you can't do some load memory into your SIMDRAM control unit.
Can I execute another micro program depending on?
No, you have to. The SIMDRAM control unit only executes micro programs which it gets from the CPU. It can't by itself schedule micro programs.
Right. Yeah, that's probably what you need ultimately.
Yeah, I guess what's the concept of a program counter? The program counter is just in the control unit. That's it. There's no.
So the SIMDRAM control unit basically does its thing without knowing what it is doing in memory. It's just sending AAPs and APs out to the memory controller, but it doesn't care what they are doing. So there's no way of loading data from memory into a microregister or loading or writing from a microregister, which is stored in the SIMDRAM control unit itself to memory. So it's just an efficient mechanism of generating a string of AAPs and APs. So let's get to some more discussion points. How would you think that application developers utilize SIMDRAM? Is it feasible to think that they would insert these commands by themselves? What would be the problem when the user doesn't have SIMDRAM? What would be the complications?
Okay. Yeah, I think it would be feasible to do it by yourself, because currently also you could also do SIMD by hand with native instruction. What I think would be a little bit of a problem is if you say you have a function that adds two arrays together, that gets passed in a pointer to memory from a user that uses this function, like in a library. Then you would have to know if this memory location is vertically or horizontal, right? Or you would have to have a way of detecting it, or you have to do like a memory copy to ensure that it's vertical. So I think this would be also a problem that has.
So to ensure that the data is stored vertically, you just have to execute that command before you write the data into that location. But yeah, if you don't know how the data was written into that location, then you would have a problem, sure.
So if you execute this command to say that should be vertically, then it will detect
only new write requests will use that transposition buffer.
Let's say we have an array that's stored horizontally, and then you say, okay, this memory location is vertically, then it will mess up the data, right? Because it treats it now as if it were vertically. Or
yeah, that's correct. Yeah,
okay,
you would have to write that data into the memory location once again, I think. Yeah,
I think that would be, for this, I think you would have to have a like an instruction that fetches from the buffer that stores if a memory location is vertically or horizontally to know if it's vertically or horizontally. Currently.
Yeah, and there are also some other problems which I haven't mentioned yet, but you have to pin the data in memory, the pages, so that you don't have them in cache, and to ensure that the data you read then is coming directly from memory and not served by the cache.
So even with normal SIMD operations, what can kill you is if you have SIMD operations and then you have one instruction, just one or two things that you can't do properly with SIMD, and then you have to convert everything back and then do the one thing and then convert it back to SIMD and then continue.
But the good thing here is that once you have the data laid out vertically in memory, you still, for the CPU, it still seems like it's laid out horizontally. So you can still do stuff on it. You can still change elements.
Right. What kind of a latency does this transpose? This is just a general question, but what kind of latency does this new transposing introduce in general?
I actually don't know. Sorry.
Okay. Because you do have to look up if something is or isn't vertical or horizontal. So that's
that's just like some like equality checks. Shouldn't be too big of an overhead.
I think the bigger problem is that you have then, if it's laid out vertically and you want just to check, let's say a 46-bit number for equality, to do like a jump or something while doing this, or in between doing this DRAM SIMD, then you would have to fetch all 64 rows to get this one number, right?
Yeah, that's correct.
Yeah, I think that would be the bigger latency, not the translation or the lookup, but having to fetch so much memory just to compare one number.
This is a bit. Do they mention how they will handle cache coherence? Cache coherence is the wrong word, but basically, if the CPU is operating on one part of the application and it offloads one part to the SIMDRAM system, the data in the SIMDRAM in DRAM will change, and the CPU has no idea of what changed.
It's part of the programmer's responsibility to ensure that the pages are pinned in memory and thus are never stored in cache.
Okay.
So while you're doing SIMDRAM computations, you have to pin them to memory.
Sure.
And during this, the CPU is idle, right? It waits until the
it stalls until the SIMDRAM control unit is finished. Yeah, let's go to the next question, maybe. How would you imagine that SIMDRAM can be scaled so that more operations can be performed in parallel. I really think that you could scale it up even more by doing, in many of those subarrays, doing computations at once. I think we should be able to get a much better performance that way, but I'm not sure what currently is the problem there. I mean, it depends on how big the data set is. But if your data set is big enough, you could probably do computations in many of these DRAM subarrays at once. But the SIMDRAM control unit could become one of the bottleneck there at some point.
Even if you have multiple SIMDRAM units, wouldn't the bus be the bottleneck then? Because you have to like issue multiple control signals at once.
Yeah, sure. The other would also be a problem, but each of those giant computations, each of those triple row activations would only be around the size of a write or a get, right? So at the same speed which you can write or read data from memory, you could do massive subarray row-sized computations there.
Okay. Yeah. So it doesn't fill up like the whole control bus for issuing these commands currently.
Like it is right now, I don't think so. No.
Okay.
But if you scale it up, that would probably become a bottleneck at one point. And then the typical question: would SIMDRAM make sense for consumer hardware, or only for servers, specialized equipment? I really think that because the overhead is so small, and I mean, you only need some special DRAM chip and a small CPU extension, that it could make sense even for consumer hardware, especially now that neural networks are much more common in consumer hardware. And I guess database queries could also make sense.
I think one concern for this question is what happens to other application while one of the core is issuing SIMDRAM. Is then the whole memory is the whole memory transfer, is this blocked for this amount, or could you have this in parallel?
No, I don't think so. Shouldn't be blocked.
So if it's
just like a normal read or write request, but instead it's an AP or an AAP.
Yeah, I think it
just
if it
one subarray is busy doing the SIMDRAM computations.
Yeah, if it's not blocked, then I think it. Yeah, I don't see any points that would go against this. Yeah.
Can you go back to the row diagram in which you were showing the row organization?
So vertical data like this, or?
No, this one. So the operation is happening in B rows, right?
All of the triple activations happen in the B group, yes.
Yes. So yeah, this is a bit, I don't know. If you constantly keep activating those rows close to each other, isn't that like going to lead to RowHammering one of those?
Yeah, they even mentioned that RowHammer could potentially be a security implication here.
And then you have this in consumer hardware, and yeah, that's.
But they also like proposed solutions they refer to.
Okay. Sure.
So other solutions for RowHammer can also be applied here, which seem to solve the problem. Also with SIMDRAM applied.
Okay. Yeah.
Is there also a mechanism proposed to for like the end user to ensure that that memory that he has allocated is in one unit that can be computed? So it's so that does it.
Currently, there's no mechanism ensuring that you do your memory allocations at the correct positions. In the simulation, they just forced it, I think, to specific memory locations in a single subarray.
Okay.
But yeah, that was also one of my weaknesses, that memory allocation is still an unsolved problem. But let's go on. What are the options for solving the memory allocation problems? I was thinking of having maybe like a special malloc here. So for CUDA operations, there's already a special CUDA malloc, which can, in specific cases, allocate shared memory, because nowadays you have systems like Apple processors which share memory between CPU and GPU, and then CUDA malloc probably uses that shared memory. And I guess we could have like a SIMD malloc, which ensures that the allocations are laid out properly in memory. But at the same time, how would it know which of those operands are needed together? So we need, like, maybe we need to recreate an arena first, like some allocator, which we then can allocate some limited number of arrays in that subarray.
Yeah, I think so. That would be probably the easiest for the operating system to say, okay, each call has a guarantee that all the memory is in the same bank, but as soon as you make a second call to request new memory, then it hasn't any guarantee, and so you have to
maybe like one call which creates a memory area, which would refer to some subarray, and then you could tell the CPU or like the C standard library to allocate a block in that area of memory.
What would be the limiting size, or the size current DRAM chips that you could operate at once? So
SIMDRAM, so the size of a row.
No, so the entire matrix size, basically. So if you have
entire subarray, I think it's a few kilobytes. I'm not entirely sure.
Okay. Yeah, then probably you also would have to have a mechanism to, if say you have two large arrays you want to operate on, you have to like copy them from one
but rowclone also has a mechanism for inter-subarray copies. And then obviously, can we make it easier to define custom microprograms? I really see the possibility here to define custom microprograms based on a per program basis. So it would analyze a C code or like some special C code compiler, which compiles into microprograms, which are then executed on demand. So during the compilation process, we could generate a microprogram using that three-step process, store it somewhere in the application binary itself, and then when needed, we could tell the CPU that we want that microprogram to be executed. So that not the hardware vendor defines which microprograms are included, but the applications developers could do that by themselves. So I see a lot of parallels to GPUs here. At the beginning, GPUs also had only a limited range of operations, but nowadays we have programming languages for GPUs. And have custom GPU programs which are transferred on runtime to the GPU. Would you think that like such a system would make sense?
I mean, these microprograms that we're using now are already.
Geraldo just wrote that a subarray is around 8 megabytes of size. I'm sorry for.
The microprograms that we're using already are kind of like instructions, right? Sort of.
At the moment, they are instructions, yeah, which tell the SIMDRAM control unit which program to execute.
So what kind of additional microprograms would we even need?
Like we could have the kernel directly implemented into a microprogram for operations which only our program needs. So let's say an addition operator which adds 2 arrays and adds 3 to each element. We could have that in a separate microprogram without us having to do 3 SIMDRAM calls to do that.
Right, and since that just activates, we can ultimately just solve that ourselves and then save that somewhere.
And then more triple activation optimizations could come in and make the program more efficient, maybe.
Yeah, ultimately we'd probably have to do it the way that you said, where you have this like a section of the binary that you just utilize to store these microprograms.
Maybe yeah, it's pretty similar to how GPUs are already programmed, right? Where you either compile it up front, but then let the implementation of the GPU vendor compile it again, or you have some intermediate representation stored, or just the plain old GLSL program, which gets distributed together with the binary. And I could imagine something similar for SIMDRAM. And in the long future, of course, long term. Right. And then how would you imagine the future of processing using memory? How would you imagine that to look like? Do you think that it will gain traction? I mean, if it's so much more energy efficient and in some cases so fast.
I mean, the only question that comes to mind is that it's really great for bulk operations or parallel processing, but if you have an application with a huge context, for example, it uses 60 registers, how do you access 60 registers? I mean, how do you access 60 values concurrently in such DRAM based, and even in this system?
I mean, there are also always regions of the program for which you can use SIMDRAM, and there are regions which you can't use it for, where it doesn't make sense.
Yeah, so you're basically saying that, okay, the future is heterogeneous. We can't get rid of the CPU. We have to design both together. But I'm thinking more in terms of like offering processing using memory as an exclusive solution. But yeah, of course, this is a philosophical discussion. Anyways, thanks.
The problem with the heterogeneous use is really that while you can access these vertically stored data normally from the GPU, from the CPU side, you can't do it efficiently, right? It's slower because if you read 64 bits in a vertical layout, then you have to do these 64 accesses. Or am I misunderstanding something?
Yeah, it's slower at least, yes.
So you can do either or, but if you have a program which you have to choose between one or the other. Either the CPU can do stuff quickly or SIMDRAM can do stuff quickly. And if you want to do both, then you would have to somehow transpose this memory and then do the SIMDRAM and then transpose it again and then do the CPU and just copy memory around constantly, basically.
Yeah, and of course, all of the benefits of having a caching system also get eliminated if you always do stuff in memory. Because while you're using SIMDRAM, you can't use the cache for accessing any of that data.
I mean, I suppose technically you can do this transposing using this transpose unit, which is probably close to memory, right? So you don't have to go through the whole pipeline if you somehow added a transpose instruction somewhere.
Oh, sorry, say again. Like a transpose.
The transpose unit sits between the cache and the memory, right?
That's
so you
correct,
don't
yes.
have to go through the cache if you want to transpose this memory.
But still, you have to do a normal memory access all through DRAM to access those elements. Whereas normally you would load some area of that into your cache and into your next cache, and then maybe the first access would be slow, but the following accesses would be faster. But while that page is pinned in memory in DRAM, all of those accesses would be slow because they would need to issue read request to DRAM.
Yeah, so you could have this array twice in memory, which is an idea we heard earlier, basically, where you could have it twice, where you have it once and untransposed and once you have it transposed, and then you would just have to transpose it back when you want to do.
I mean, having two copies in DRAM isn't really a solution, because it's not the time that takes to transpose, which is the problem, but also that you can't use the cache for all of those accesses.
Right.
If you still can't use the cache, you still have a slow system.
But you only have to keep those that part of memory pinned, which you're using to do SIMDRAM, which is the transposed section. The
But then
section
if you wanted to do SIMDRAM again, you would have to copy from that untransposed part to the transposed part and would go through the translation buffer again, right?
You'd have to properly flush the cache first and then go through the transposition. But at least you'd get the cache benefits while you're doing the CPU instructions.
But you could also unpin that page, and then the transposition unit would be used to untranspose it, and then you could use it in your cache.
Right, yeah.
I don't see the benefit of having two copies in memory.
You have to untranspose it in blocks or somehow.
Yeah, I'm not really sure if there's any benefit of having it twice, because that's already what the transposition unit is there for.
Yeah, it's more of a hack on my lack of understanding.
Yeah, perhaps to come back to your question, I think it heavily depends on how well memory processing near memory is doing. So I think probably one of those two solutions will eventually win out, and we will have one of those two heavily used. But yeah, I think it heavily depends on.
But in the long term, we need to do more of a computation in near memory or in memory, right?
Yeah, exactly. Yeah.
Because otherwise we don't get as many performance gains in the CPU itself. Very interesting, thanks. Any other discussion points?
I want to add something on top of the discussion that just happened about the transposing unit. Can you hear me well?
Yeah, sure.
Okay, great, thanks. So I think the discussion was really nice, but we are forgetting the scope that this paper exists, or the scope of processing memory in general, which we start from the assumption that the application is memory bound. So application really suffers from accessing a bunch of data from DRAM because the data cannot fit on the cache, or because the access pattern does not have enough spatial temporal locality to reside on the CPU. So we already come from this assumption, right? If you assume that this is the case from the start, and this is the case for many applications, real applications, then transposing the data, the overhead of transposing the data is extremely more amortized, because this ping pong that you guys keep talking about of do some computation here, transpose, then go to the CPU, do the computation there, transpose, going back and forth. This shouldn't happen, right? Otherwise, why are you using the system at the start, right? It's just like, of course, you can do it as a programmer, but it's the same thing as I give you a GPU, and then you're going to start to implement an application with a bunch of branches and jumps and crazy stuff, right? That device is not target for this architecture or this type of access pattern, right? So this is the case. There are some cases that this type of ping ponging is a problem. And this is, for example, related to the float point unit or float point computation that we don't implement in SIMDRAM, right? If you think about it, the problem, let's assume that you can solve the problem of the sorting across bit lines, but then there is a problem that for every time that you need to normalize the matrices, or you need to normalize the exponents, you need to bring the data to the CPU or to transpose units, to the CPU control units, transpose the data all again, one by one, figure out which decimal value you have in the end, and then issue the amount of exponents that you need to, the amount of chips that you need to do in DRAM, which is extremely costly, and goes a little bit against the paradigm that you are working on. So this is, I think, what I want to add. And the discussion about processing using memory or processing near memory, I think, is also quite interesting. I don't honestly think that that is a clear winning, or there is going to be a clear winning in the future, because they serve as different purpose. So since you are inside DRAM, or sorry, if you think about the DRAM organization, and if you just draw a point at each point of the design or the circuit, you're going to find a different memory bandwidth available for that particular area, right? And I don't know, from the bandwidth of a subarray is much larger than the bandwidth of a bank, that is much larger than the bandwidth of a I/O, which is much larger than the bandwidth of available for the memory controller, right? So there is all of this problem. And if you want to accelerate memory-bound applications, let's say that processor near memory is employed, at some point, you're going to hit again a bandwidth wall because the applications just keep growing in data volume, and as much bandwidth they can provide, likely a programmer is going to find a way to exploit it. So you constantly need more and more bandwidth, and pings are more and more expensive to include in the system. So at some point, you're going to need that bandwidth available in the subarray, and all of those mechanisms are already processed using memory, right? We are talking about exploiting the organization of the subarray, exploiting the DRAM cell to do some computation. So if you already have something like, let's say, UpMem that Juan presented in some lectures ago, or some modern processing near memory solution, you already have the DRAM. You already have the capability of enabling SIMDRAM or Ambit or RowClone. It's just a matter of coordinating the computation accordingly. So there is no reason why not to do it, other than some limitations that we still need to fix as related to programming or as related to coherence or virtual memory type of things. But we can all solve those problems. But once those solvers are done or are solved, those both solutions can coexist in a system without much of a problem. So yeah, I don't want to extend this much longer. So just want to add on top of those. Is there any particular question that was not answered? I think I can, if you guys are still curious, I might be able to answer them.
Yeah, thank you very much for your comments.
Welcome.
Okay, I guess then we are finished with the discussion. Thank you so much for listening. This was SIMDRAM.
Yeah, thank you very much, Lucas. Very good presentation. On top of what you presented and what you guys discussed, and also the comments from Geraldo, yeah, I would like to add that this is a path that is just starting. This is definitely a promising direction, and hopefully we will keep doing research in this direction in order to enable more functionality and more flexibility to the substrate. So if you guys are interested on the topic, please talk to Geraldo and talk to others in the group, which for sure will be glad to work with you. Thank you again, Lucas. Good job.
Thanks.
So I think we come to an end. Thank you so much, Juan. I'd like to thank Fiona and Lucas, all the mentors, Nika, Juan, and Geraldo, all others. So we had to end up the lecture for today. Don't forget to take the quiz. It's already available online. And thank you so much, everyone. See you next week. Please stay healthy and safe.